All right, good morning or good afternoon, guys. Today we are going to be finishing up one of our last lessons for Module 6. We are working on a different standard today, and it kind of flashes back to 7th grade as well, about probabilities of compound events. So the standard we're working on is 8SPA4, Understanding Patterns of Association in Bivariate and categorical data by displaying frequencies and relative frequencies in a two-way table. We've already kind of covered that. So what we're really focusing on today is more the compound events. So interpreting those kind of things and summarizing them. All right. By the end of this lesson, you're going to be able to determine how many possible outcomes an event is likely to have based on the choices in the variables that you're given. So you'll know you're successful when you can use organized tables, tree diagrams, and the counting principle. We're going to have 3 different strategies today to determine various outcomes of compound events, as well as the total number of possible outcomes for a compound event. Okay? We're going to get into some examples and exercises. You'll work a little bit in groups today. Close out the lesson and you'll do the exit ticket and reflection on your own. And as always, please make sure your video's on, your mic's muted, you're showing your thinking and your work, you're participating when you're in breakout rooms with your group members, you're having appropriate conversations in those breakout rooms. You're letting me know any technical issues you may have as soon as you encounter them. You're staying respectful, responsible, and safe. And if you have a class job, please make sure you are fulfilling those responsibilities as well. Okay, let's get started. All right, before we get into this lesson, we want to just go over a little bit of background and vocabulary and knowledge. So the first thing I'm going to talk about is a random sampling. So what is a random sampling? Let's look at this, and I just want you to highlight whatever I highlight. It says a sampling technique in which each sample has an equal probability of being chosen. A sample chosen randomly is meant to be an unbiased, highlight that, representation of the total population. So these are the key things I want you to look at. Equal probability and unbiased. That is what makes something random. It is very fair that pretty much everything has an equal opportunity of being chosen, and there's no bias, right? We've talked about this before, but something that's not a random sampling would be, well, you know what? Let's just go over these questions below and see if any of these would be considered a random sampling. If they have an equal probability of being chosen, each of the variables, and if it's unbiased. A, you want to know what most people prefer doing, watching cartoons or movies. You survey your 4 younger siblings. Do you think that that is a random sampling? So these are the people you're surveying. 4 younger siblings. If they like to watch cartoons or movies more. Well, in my opinion, this would not be a random sampling because there's going to be a little bit of bias. If you know children tend to like cartoons a lot more than movies. And so there's probably not the most equal probability of being chosen because your 4 younger siblings might all have a lot of the same likes or dislikes because they grew up in the same household. They're also younger, okay? So probably not A. B, it says you want to know if most people prefer breakfast or dinner. You ask every 4th person who leaves IHOP. This would definitely not be a random sampling. There's a lot of bias because you already know that these people like breakfast. They're coming out of a breakfast restaurant. So this is not a random sampling. It's very much targeted. Okay. C, you want to know what brand of shoe most people prefer. So we're looking for the brand of shoe. You ask every 10th person you see at the mall and sample 100 total people. This is a random sampling. This is the one that is random because it's unbiased, right? You don't know these people. You're not choosing them based on, something that might lead their decision a certain way. And you're doing a lot of people. 100 total people is a lot, okay? So that's just to go over that word random sampling. You will have a question like that on your test that asks you to identify a random sampling later this week. Okay? All right, moving on. Today's lesson is about counting outcomes. What does it mean to count outcomes? When you have 2 or more independent events, you want to determine how many possible combinations of events there are. You do what's called counting outcomes. Okay? Here's an example of a question we might see today. You have 3 shirts, 2 pairs of pants, and 4 different shoes. How many different outfits can you make? So this is what we're going to be doing today. This is the type of question we might get. And there are going to be 3 strategies that we use: creating a combination table, creating a tree diagram, or using what's called the counting principle. All right, let's get started. All right, let's start this lesson off. What I want you to do here is just write down the things I write down and just really observe me before we get into practice later on, okay? So again, if you have questions here, just watch and listen and try to take it all in. It says, you're interested in buying flowers from a florist. You ask the florist, what type of flowers do you sell? The florist tells you that they sell tulips, roses, sunflowers, and daisies. So they sell 4 different kinds. You ask the florist, what types of pots do you sell that I can purchase? The florist says they sell brown pots, yellow pots, and green pots. If you want to buy one type of flower and one type of pot, our question asks us, what are the different options you have to choose from? Okay? So to begin these questions, I always do my highlighting. Of course, you want to do some close reading. And then I want to identify my variables. So I have 2 variables here. This is my first variable. This is my second variable. So the flower type, there's 4 different types of flowers to choose from. And our pots, there are 3 different pot colors. Okay, so we have 2 variables, and each of those has a few different options. Okay, from there, I want to identify the strategy I should use. Well, we don't know the different strategies yet. I haven't taught you them, so I'm going to show you all 3 different strategies. So the first one I'm going to show you is a table. The second one I'm going to show you is a tree diagram. And the third one I'm going to show you is what we call the counting principle. Okay, we use these different strategies at different times and for different reasons. All right, and the first one is the table. And to make the table, we just list out our variable options on the top and the side and create basically a combination table. So we have 4 different flowers. We have tulips. I'm just going to use a T for tulips. Roses, R for roses, S for sunflowers, and L for lilies. Okay, and then on the side, we have 3 different pot choices. We have brown, yellow, and green. Okay, from there I'm just going to line up some lines, some columns and rows so that I stay organized. And then I'm going to list out all the combinations within these cells. I'll do it in green. So the first combination cell, we have T for tulip with a brown pot. So I'm just going to put tulip in a brown pot. Then we have tulip in a yellow pot, tulip in a green pot. Okay, we have rose in a brown pot, rose in a yellow pot, rose in a green pot. Sunflower in a brown, sunflower in a yellow, sunflower in a green, and a lily in a brown, lily in a yellow, lily in a green. So now we can see all the different options we have. We can count how many. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different options. And we can see them all out. Maybe you wanted to see them all out so you could make a better choice of which one you wanted. Okay? We cannot use this option if there's more than 2 variables. So for this, we had 1, 2 variables. If we had a third variable, we wouldn't have anywhere to really put it. It would just kind of start to get really disorganized and convoluted, and it just wouldn't be as efficient. Okay, moving on to a tree diagram. Tree diagram, we essentially do the same thing. We're going to list out our options, okay, for our first variable: tulip, rose, sunflower, lily, and then we're going to list out our other options, but now as branches for this one. So for our tulip, we have 3 different options that come with it: brown pot, yellow pot, green pot. For our rose, we have 3 different options that come with it: brown, yellow, green. Sunflower, same thing: brown, yellow, green. And lily, 3 different options: brown, yellow, green. So this is essentially kind of like branching out. And to find out our different number of options, we can count our bottom row. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 in branches. So that means there's 12 total options, which is the same thing we identified with our table. And you can see your options by just going down your list. So you could say, okay, a tulip with a brown, tulip with a yellow, tulip with a green. And just, you can see all the different options that you make here. Okay? This one is used maybe when we have more than 2 options, but definitely when we want to see what our options are. Okay, so if your question said, what are all the options you could make, instead of how many options you can make, you would want to use this. And lastly, we have our counting principle. We use this when we just need to know the number of options. We don't need to know anything else. So if we need to know how many options can you make, not what are the different ones, we can use this strategy. And basically you list out the numbers for each variable. So we had 4 different options for our first variable, and we had 3 different options for our second variable, and we just multiply them. 4 times 3, 12. We have 12 different options here. We don't know what they are with this principle, but we can just tell you how many we have. So these are the 3 strategies that we're going to be using today. There's a time and place for each one, and we'll decide that as we go. But please make sure you have this down so that we can reference it throughout as we move along today. Okay? All right, example 2. You've won a contest at a car dealership and you're going to get a free car. The dealership is randomly going to select the car that you get. They're going to decide your engine by flipping a coin. It could be a 4-cylinder or a 6-cylinder engine. And they're also randomly going to select the color. There are 4 options: white, green, blue, and red. What are the different outcomes, all of the different outcomes of your new car? Okay, what are all the different options you could get? Let's look and see which strategy is probably best to use. Should we use a table, a tree diagram, or the counting principle? Well, if we need to know all of the different outcomes, then we cannot use the counting principle, because that's just going to tell us how many outcomes, not all of them. It's just going to say, oh, you have 15 options. It's not going to tell us what those options are. So we can either use our table or tree diagram, because both of these are going to work. So I'm just going to show you both. So the first one is our table. We have a 4-cylinder and a 6-cylinder as one of our options. And then our color options are white, green, blue, and red. Okay. So we can either get a 4-cylinder car with a white color, or we can get a 6-cylinder car that's white. You get a 4-cylinder green, or a 6-cylinder green, 4-cylinder blue, or a 6-cylinder blue, and a 4-cylinder red car, or a 6-cylinder red car. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8 options, and we can see all of those options right there in our table. If you would have rather done the tree diagram, it's pretty similar. I'm writing my longer choices, the longer variable, or the one that has more choices up top, just because it'll be easier to put this on here. So we have a 4 and a 6, 4 and a 6, 4 and a 6, and 4 and a 6 for each of these. And you can see all of your options out right there. Okay, so our options are white car with 4-cylinder, or white car with 6-cylinder, green car with 4-cylinder, green car with 6-cylinder, etc. Okay, so either of these options would have worked here, and we can see all of our options listed out, all of our different outcomes. All right, let's go ahead and move on. All right, we're actually going to start doing this one together, so please communicate with me in the chat when I ask you your opinions and questions on things, okay? It says Paula's going to choose the size, color, phrase, and picture for her birthday card. There are 2 sizes, 4 colors, 7 phrases, and 4 pictures for her to choose from. The printing company charges a fee to add extra design elements, so she will only choose one of each. How many different design cards are possible? All right, so the first thing I want to see is basically how many variables do we have here? How many different things can she choose from? Well, she has the size, the color, the phrase, and the picture that she gets to choose. So she has 4 different variables she is going to be able to mix and match to find combinations, okay? Our question doesn't ask us what are the combinations, it just says how many. So this is going to affect which strategy we choose. Off to the right it says, should you choose a table, tree diagram, or the counting principle? Well, we can't choose a table because we have more than one variable, or more than two variables, sorry. So it can't be a table. We could do a tree diagram, but this is going to be a huge tree diagram, right? It's going to be so many branches on this thing, it wouldn't really make sense because we don't need to see all of our options. We just need to know how many options there are. So the one that's going to make the most sense to use here is the counting principle. So remember, the counting principle is we're just going to multiply our numbers together. So we have 2 sizes, 4 colors, 7 phrases, and 4 pictures. So we're just going to multiply all these numbers together. It doesn't matter where you start because order does not matter when we multiply, right? So I'm just going to start at the beginning. We have 8. Then we're doing times 7 times 4. 8 times 7 is 56. Is 224. So how many different options are possible? After you multiply all your variables together, you see that there are 224 options possible. Okay? It would have been terrible to make a tree diagram because that's how many branches we would have had at the very end. Okay, not even counting all the ones we would have had before then. All right? So that's why this counting principle is very important to use when we only need to know the number of outcomes, not what each outcome is. Okay, let's continue on. All right, exercise 2. You're at a clothing store that dyes your clothes while you wait. The store offers 4 different articles of clothing in 3 colors. So we have 2 variables here. 4 different articles of clothing and 3 different colors. If you randomly choose the article of clothing and the color, which of the diagrams can be used to find all of the possible outcomes? So I want you to take a second, look at these 2 different tables and decide which one is correct, which one matches that, which one would we be able to use based on the description above. Message me in the chat when you think you know whether it is diagram A or diagram B that we can use. Okay? All right, let's look at these diagrams. Diagram A has our colors listed up here. There's 3 color options, blue, orange, and purple. Diagram B has the same thing. They just list them as purple, blue, and orange. Okay, so the order's different. For diagram A, we have our 4 different clothing options, socks, hat, pants, shirt. And we have the same thing over on diagram B, just in a different order, shirt, pants, socks, hat. Each one of these blocks, or cells we call them, has our combination. So this one is in the blue socks position, so it says blue socks. This one's in orange socks, so it says orange socks. Okay, and the same with this table over here. You'll notice they are lined up correctly. All right. So what's the difference between these 2 tables? If you study them close enough, you'll notice they have all the same outcomes. They're just listed in different orders. Is that all right? What do you guys think? Would both of these tables work? Yeah, absolutely. So I just wanted to show you this to prove to you that it doesn't matter the order in which you write things for your table. As long as you list them out, you're going to get the combinations. For example, orange pants is all the way over here on the 3rd column, 2nd row. Orange pants is over here, 2nd column, 3rd row. We still have it. It doesn't matter. We still see the outcome. Okay? So both can be used to find the outcomes in this situation. All right? Let's continue on. All right, exercise 3, I'm going to have you guys try this together in groups. It says, Elise is going to buy an around-the-world plane ticket. She will get to see just one city from each continent she will visit. The following table shows the continents on her trip and how many cities she can choose from each continent. How many different combinations of cities does she have to choose from? Right now, you're going to be sent to groups. What I want you to do is 2 things. First, decide what's your strategy. What do you want to use here? Tree diagram, table, or counting principle? So pick a strategy together. And then from there, I want you to actually find out the answer. So in your groups, I want you to tell me what is her, how many different combinations does she have? Okay? You're going to have 3 minutes in your groups to do this before we come back together. Please, everyone needs to have an answer, and I want to see maybe how many groups can get this correct. once we come back. Okay? Go ahead and join the breakout groups I've invited you to. All right, let's go ahead and go over this. She gets to choose one city from each continent. So for Europe, she can only choose one city. She has 10 options. For Asia, she can only choose one city, but she has 8 options. Africa, 4 options. And Australia, 3 options. Okay? So we're going to take all those options together, and we're going to figure out how many different combinations she can make. Now, if we're just looking for the number of combinations, not what the combinations actually are, then we do not need to do a table, and we do not need to do a tree diagram. We can just do the counting principle. That is our strategy we should use. Okay, so you should have identified that with your group. The counting principle. That is our strategy here. And the reason being is we can't do a table, right? There's more than 2 variables. And to do a tree diagram is just kind of unnecessary at this point because we just need the number of options. Okay, so let's go ahead and figure this out. We have 10 choices for Europe, 8 choices for Asia, 4 for Africa, and 3 for Australia. And we're just going to multiply these out. 10 times 8 is 80. Okay. 4 times 3 is 12. And 80 times 12, let's do this in our calculators real quick. 80 times 12, I get 960. So how many different options does she have? 960 options or combos that she has. And you should probably understand why we should not have done a tree diagram here. We would have had 960 final branches to our tree diagram. It's just not feasible. Okay? Hopefully you guys got that right. We're going to try one on your own now. Let's move on. All right, I want you guys to try this one on your own. It says, John always wears a shirt, pants, socks, and shoes. He owns 12 pairs of socks, 3 pairs of shoes, 5 pairs of pants, and 5 shirts. How many different outfits can John make? Okay, I'm going to have you do this on your own. I'm going to give you 2 minutes to do it because that's really all that it takes. First thing I want you to do is to choose your strategy. Okay, and be able to explain why you chose the strategy you used, and then give me the answer. How many different outfits can he make? Go ahead and begin. All right, the first thing we needed to do here, or you needed to do here, was identify what strategy you should use. So the first one is our table. Should we use a table to do this? What do you guys think? Let me know in the chat, yes or no. All right, we should not use a table, and the reason is there's more than 2 variables. For tables, we can only do 2 variables because we have that top and the side. Okay? Should we do a tree diagram? What do you think? Yes or no in the chat. And what would be the reason why we would not do a tree diagram? Well, we just need to know how many different outcomes he can make, not what they each are. We don't need all that info. And it would take too long to make. Okay, so we're going to use the counting principle. The reason why is that we just need the number, not each individual option. Okay, so if we're just needing the number, we are going to just multiply our variables together. 12 times 3 times 5 times 5. Okay, 12 times 3 is 36. 5 times 5 is 25. 36 times 25 in my calculator. Remember, order doesn't matter, so if you did it a different way, you will get the exact same answer if your math is correct. We get 900. So there are 900 different options for this situation, okay? Hopefully you got that correct. Hopefully you feel confident with this stuff, and hopefully you can identify which table is good to use and where. Okay, let's move on. All right, let's close this lesson out and see if we are good to go for our exit ticket. So to summarize, it says, When having to count the possible outcomes or combinations for different situations, there's 3 strategies we can use. So we talked about 3 strategies today: creating a table, a tree diagram, or just using what we call the counting principle. Let's look at the table first. To create a table, we list out all of the possible variable options and then each various combination that would go with them. It's best used when there are less than 3 variables involved. So maybe we had a situation where they said, okay, I have 3 shirts to choose from: a red shirt, a green shirt, a blue shirt, and I have 2 pairs of pants. Or I can use shorts or pants. Okay, this would be a great one to use if we had to know the different options for outfits they could make, because we could easily create a table. There's only 2 variables. We would have SR, PR, SG, PG, and SB, PB. Okay, and then we would have all those different options in the middle, and you just have to remember what your little letters represent. If it's hard for you to remember what they represent, just write out the whole word. Okay. Next, we have a tree diagram. With a tree diagram, we list out all of the possible variable options and then create branches for the next set until you have accounted for each and every choice. The last row represents the total number of options you have. Okay, here's an example for this. Say we have 3 things to choose from: our shirt color, our type of pants, and maybe our shoes. So we have those red, green, blue shirts, and for each of those we can choose either shorts or pants, shorts or pants, shorts or pants. And then from there we can choose flip-flops or sneakers. It's going to be hard to fit all these. And this was only 3. And so here is my tree diagram for this, so I can see at the end that I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 total options. And our options would just be listed like this. Here's 1 option, 2 options, 3 options, 4 options, 5 options, etc. Okay, we just follow our branch all the way down to the end. Okay. Last option that we have for a strategy to use when we're doing this today is called the counting principle. And forever just ask to identify how many combinations there are, not what each and every single combination is. We can just use this, okay? So for the case of this one above, we had 1, 2, 3 different options. The first one had 3 variables. The second one had 2 variables. The third one had 2 variables. So if I just multiply these together, 6 times 2, I would have had my total number of options at the end, which I did. There were 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 total combinations. Okay, let's go ahead and move into what your exit ticket is going to look like. All right, your assessment for today. If you feel confident, if you feel like you're ready to move on to this right now, please move into it. It'll be in Galileo. You have 3 questions. The first one is a situation about deciding a plant. It tells you the different kind of plants and the different kind of pots, pretty much like our first example, and you want to know how many different combinations are possible. Number 2, these people are going to buy some new furniture. They want to buy a couch, a table, and a recliner, so they have 3 different things. They've narrowed it down, so they're choosing between 4 couches, 5 coffee tables, 9 recliners. How many combinations are possible? And then the last one, it says it's make your own dish night at your favorite restaurant. They offer 5 types of pasta, 4 different sauces. You get to choose one of each. Which of these tables would help you find all of the different outcomes? Okay, so you're going to look at these tables closely and decide which one is correct and matches this situation. When you're done with your exit ticket, please do the reflection question that is posted in Google Classroom and then begin working on your weekly work. As always, if you don't think that you're ready for this exit ticket, go back and start rewatching some of the video to get a little bit more confident before you begin. You can always use your notes for your exit ticket as well, and you can reach out to me in the chat if you have specific questions that I can help you with, okay? Go ahead and begin on your independent stuff. Good luck.